Dzień dobry, good morning. Na imię Cosimo. My name is Cosimo. The webinar will be in English because my my Polish is very basic. I'm as Lukasz told me is hello. Can you hear me? Yeah. Okay. My name is Cosimo. I am a tunnel and geotechnical team leader in AYESA, international consulting based in Spain. And as part of my technical work, I am also collaborating with Midas to develop the new features in Midas GTS. In particular, Midas is, as you know, is a complex, I would say, a package of different softwares, and I am one of the so-called tester, people who are chosen by Midas to carry out some particular analysis, and to also to carry out double check about the algorithm and the structural calculations. Today, our webinar is regarding the solid structure interaction for piling foundation in Midas. I hope you can see my screen. The structure of the presentation is, is very elastic. In each moment, if you have some doubt or if you have some concern, we could go deep the models. I have the models in my computer, so we can go and we can speak about what are the some trick to carry out I would say an adequate design. And the index is very simple. It's how to design a piling and a pile raft foundation. In particular, in this is very important. In particular, in countries, for example, like Poland, but in general, most of the countries where each day we are doing more and more infrastructure, and the space allocated for this infrastructure is each day less. Then we will carry out a comparison between the numerical analysis versus the analytical solution. Then I will bring to you a case study of the substructure in GTS, and then we could speak about the structural soil model, the rigid, the flexible, when we have to use, or when it's when I would suggest to use hinged or pinned piling with raft, and then a conclusion. First of all, I would like to tell you that if you don't understand my English, I can try to make you understand. If you want to enter in the model, if you want to see something in particular, we could stop the presentation or the webinar in each moment, and we can allocate it. Okay, the piling and the pile raft foundation is very easy. In particular, in our standards, the Eurocode for people who are living in Europe, they clearly detect two ways of working of piling. Piling which mainly work for shear resistance at the lateral skin friction, and then piling working for base resistance. The calculation and the optimal solution is that a pile should work 50% for shear and 50% for base. This is the optimal configuration. It's likelihood to that this configuration is really happen than in reality. Something I would like to highlight because it is very important for our analysis is the way of base resistance. Clearly, there are different ways, as I can. I try to summarize here the most important. This is from this figure is taken from the design recommendation for Eurocode 7. Why this is this base resistance is very important, because if we choose, depending on which formulation we are employing, then we have to be consequent in our analysis. So the first step is our numerical analysis, depending in Midas, GTS, in 2D, 3D, or whatever, has to be most of the time in accordance with the analytical formulation. Then our finite element analysis is helpful, because we can lose some of the assumptions are made for the analytical solution. Regarding the piling and pile draft foundation, there are several authors who tried to summarize a good criteria for designing the combined piling and draft foundation. In my opinion, the best is, I use in my daily work the German recommendations. Here are two extracts of this paper. Regarding how it should work, the combined pile raft foundation, and when it is adequate to carry out this type of foundation, and also the features of this foundation. In particular, it is important to underline that according to the Eurocode 7, the geotechnical category 3 may be assigned for the design of a combined pile raft foundation. This is important because some countries, for example, my own country, Italy or UK, they do not allow this geotechnical category 3. They allow category 1 or category 2. This is also important, the ratio called alpha between the resistance for the piling in opposite to the total resistance of the solution. Is the piling the resistance for piling foundation is 0, means that the foundation is a spread foundation, direct foundation, or it is 1, means that it's a pure piling foundation. Which value to use? According to Paulus of 2000, of the publication of 2000, we should use between 0.5 and 0.8. In other words, piling should work more than the correspondent raft foundation. Regarding the design process, we have to highlight two clearly design process. One is the so-called concept design, which is the feasibility of pile raft foundation. The first question is, it is adequate? It is not. And second is the estimation of the required number of piles. This can be done easily with an Excel spreadsheet. It's not needed to enter in numerical analysis. And then we have the detailed design. This detailed design, the target of the detailed design is the spacing of piles. In general, the space of piles in combined pile and raft foundation is not linear. Is not it does not have this this configuration. Rarely this configuration can be carried out. The pile diameter, the ratio between the pile diameter and the thickness of the raft is important to study also the distribution of the internal forces between the superstructure and the substructure, and then the pile arrangement to redistribute the the settlements. At the end of the day, most of designers, in particular, based in my experience in Asia, for example, in Singapore and in Hong Kong, they use this type of foundation to correct the settlements of the foundations. So the interaction between the piling and the slab is a pure interaction regarding the yielding of the soil. If this is the case, there are some analytical and or closed form calculations. Some of them are collected in the standard of Hong Kong regarding piling, but my personal advice is to carry out a numerical analysis. Regarding the method we can employ, this is something I would say between structural and geotechnical. We have two methods. One method is the so-called substructure method. This is purely structural. This is what our colleagues they do for example, for Midas civil. In this case, each support works independently. Each support works mainly with an horizontal subgrade modulus and a vertical subgrade modulus to simulate the base resistance if the pile has base of the foundation has a pile resistance. This is a process mainly used for where our different points are independent. No, for example, this is not the case of, for example, a tower or some other cases relating to the building. No, for civil works, like for example for bridge, could work also if we are in a seismic area, like for example in South America or South Europe. This method has his problem because does not take into account the interaction between the different supports. No, and then we have the direct method. This direct method is what geotechnical engineers are familiar with. The soil is modeled as a continuous. In Midas is as a solid, and this can be used efficiently for both structure or both civil works or building or whenever we can which design we can use. Now there is I would highlight here before entering to the case study. I would like to highlight here the numerical analysis versus the analytical solutions. As I told you at the beginning, I am working for the Technical University of Madrid as tester of Midas, but I am also working in a company. No? My company, we have a lot of graduates, a lot of young engineers who are very fall in love with numerical analysis. And to carry out simple analysis, they start with a complicated or even so complicated 3D model. And in some cases, is to kill a mosquito with a tank. No, so in some cases, numerical analysis are helpful. In other cases, are not needed. I would be more specific. If we have a pile in a rock socket, so our pile mainly work for base resistance, we can go directly with a numerical formulation, and will be no. This will not bring us any surprise. No. So the axial load, for example, piling, can easily solve for well-known analytical formulas. Other different is the lateral piling, for example, for an abutment of a bridge. in particular for an abutment of a railway bridge, where we have the brakes forces due to a train. This brings different configuration to our piling, have to be studied in numerical analysis. No, when we can use one is one is good to using a numerical analysis, but for example, for to evaluate the negative skin friction. No, the classical example. I mean, according to the Eurocode, the negative skin friction has to be avoided as far as it's possible, but in some cases is very difficult. So a good approach to use numerical analysis, for example, is to evaluate the negative skin friction. There are some authors, for example, Bowles, in his book Foundations, he brings some calculation regarding negative skin friction based on the middle point of the neutral point. It is the point where here we have the negative, and starting from this point we have positive skin friction, but this is mostly related with a really important assumption, that is the pile is only axial loaded, and in 99% of piling we have axial load and we have bending moment or even the shear. So we have to watch out to use this formula. No, the same happens for the pile draft foundation. For example, regarding the settlement, what I was speaking before, most of the designers use pilot raft foundation for to avoid or to mitigate the settlement in along a pilot raft foundation using. If we are in Asia, we can use, for example, the formulas came from the manual of piling of Hong Kong of 2000, or we can use the formula of 1994 for Randolph, which is a formula which gave a very good results comparing to Midas and to numerical analysis. Then there is also the interaction between the points of the different behavior of the pilot draft foundation. No, in general, the first point is from 0 to point A. Here is working the pile and the raft as elastic. Then from point A to point B, the piling is failing, and then is only the when it's failing all of the foundation. No, well, to evaluate this this diagram, we could go through the analysis of Paulus of 2000 and 2004, or we can carry out a numerical analysis. No. So the structure of our analysis is this one. So we have, I call here structural engineer and geotechnical engineer to clearly highlight where are the competence. A structural engineer is working with Winkler springs, foundation, settlement, and stress, and passes it into geotechnical engineer. So he is working with a subgrade modulus. Most of his question is related to which subgrade, horizontal subgrade modulus has this this soil. Now, the good answer from geotechnical engineer should be it depends. It depends on what? It depends on column loads. It depends on which load, because the subgrade modulus is the value between the stress and the corresponding settlement. No? So this should be the I mean, if you want to use the correct method, this should be the flow of working. Structural engineer pass the columnar loads and the Winkler to geotechnical. Geotechnical carry out a direct method without springs, and then he is calculating the spring and the foundation, the settlement, and the stress. This should be the ideal world. In reality, this is difficult to happen. Okay, this is more or less a brief introduction to numerical analysis and analytical. So we can go to the first case study. This is a desalination plant in Midas. This has been carried out in Colombia, and it is part of a study we carry out for Midas to calibrate the different configuration. And okay, then we will maybe another webinar we can speak about the dynamic load, because in Colombia we have a really high seismic, it's really high seismic area, so it's really important to evaluate the direction of earthquake and whatever. Okay, so the structural features are that this is 45.6 meters outer diameter. The slab is 0.3 thickness. The vertical pressure on the structure is 55 kPa. This is a desalination plant, so it's 55 is constant. And the solution, the evaluation, was carried out with 69 piles of 0.6 meters with a length of 40 meters. These are the summary of the geotechnical features, are very similar to what unfortunately you have in, for example, in Warsaw or in some part of Poland. This is a material with a high plasticity. If you can see here, this the liquid limit. We are speaking about 100 versus 100 of plasticity index. The over consolidation ratio is classical of under consolidating soil, because it's going down from more or less 3 to 1. These are the values of the seismic velocity. We have about 200 meters per second in almost 45 meters. And this is the distribution of the undrained shear strength with the depth. So as you can see, is 50 kPa, more or less. Then last but not the least, this is the seismic and the vibration, the spectrum of the seismic we have to use, and as you can see, we are speaking about 1.4 G. So it's very high seismic area. No? The materials, it's evident that this material can't be modeled as more Coulomb or something different. So we employed here I don't know if you can see correctly my screen. I hope so. We were modeling it with a soft soil and with soft soil model. Soft soil model is one of the models provided in the Midas GTS, precisely to model and to simulate the behavior of high plasticity soils, in particularly where the consolidation ratio and where the undrained shear strength is not growing, is quite constant with the depth. Where in other words, where there was not consolidation during the latest 10,000 years. No. How we came up with these values? First of all, this is something very important. Comparing Midas to other software, the manual of Midas is very clear about which parameters we should include and how to calculate these parameters. For example, in other software, for example, Plaxis, this is not so clear and can lead to engineer to design or to carry out calculations with values that are not in accordance with the real behavior of the soil. No? So first of all, we have to we have some very good geotechnical investigation. We have a odometer test. We have a in situ test. We have an SPT. We have a lot of data, and we came up with this table, and we could implement this table in the soft soil model. What happens if you don't have data? I mean, this happens in some cases. I mean, if you have only one value of an SPT, it is impossible to model with soft soil. But if you have, for example, an odometer test, it is very easy to come out with the soil profile and the soil geotechnical parameters. Okay. The model was done very it's evident in 3D. The model has 150 per 250 and per 250. And how was our procedure to model? We didn't start directly from Midas because it could be could bring us more problems to understand what results are good and what's not. And we start with, first of all, the analytical calculation. Just carry out a very analytical calculation, for example, considering a round foundation pilot. Then we carry out a Celtel 3D approach. Celtel is, I mean, it's a very nice software by, I don't remember who, but I think it's Rock Science, and to evaluate the settlement in 3D. Then we came out with the Plaxis 2D, and then finally with Midas. Okay, what I'm doing here, what we can do, analytica, Celtel, Plaxis, and Midas can do directly in Midas. And I will explain later how to do it. I did it because I had to do, because we are interested in studying the different approach of the different software. No, here is more or less what we did in Midas. No, I mean, we did this, but we did in Midas at the end of the day. So we have one model. It is elastic with no piles. Why? Well, check the mesh topology and the OCR profiles. This is very important. Once we have the model, we check if effectively the OCR and the vertical tensions within the model are working. Okay. Here there is a model. We can open up later if you are interested. Then we have the elastic with piles. Okay. Now what we are going to do here, we are check the skin friction of pile and pile distribution. So we are carrying out a very high-level value engineering. We are not going through the model. We are not going to set up just to evaluate the distribution of the piles. Then we have the third model is no linear with no piles. So here we say, okay, right now we start from point 1, we go to point 3, and this is important. We check the subsoil factual law with the laboratory test implementing the consolidation. So as you probably know, in Midas we have a different type of analysis. We have the stress analysis, the seepage, the consolidation, the heat, the different type of analysis, and also we can combine this analysis in one or more set. No. And then once we check the soft soil and say, okay, more or less it is working, we were working with the no linear with piles. This is the final configuration where is implementing all this calculation. And the pinned connection between pile and slab, and agent connection between pile and slab. Okay. Darius is asking me, Zeta soil has very clear information about hardening soil, modeling with pile. Yes, hardening soil. Yes, we are speaking about soft soil. It's exactly the reverse. The hardening is where you have an increment of an increment of the resistance of the soil with the depth. For example, loading soil is widely used in UK, in London, for London clay, or for Lambeth Group, and in London. But in our case, in this case, we are using soft soil. This is exactly on the reverse. Although we are going down with depth, we are not increasing our resistance. No, so this is important because all models, including the Bohr Coulomb, the elastic, all models, they are considering a slope of increment in function more. Most of the epsilon, I mean, of the deformation, you have the different depth. No, I hope I answered to your question. Then we have how we can simulate the piling. Okay, we are in a very bad soil, as I told at the beginning, and so the piling we have to define the piling for concrete, hormigón po Hiszpańsku, concrete, and characteristic is elastic, and these are the very important. These are the base resistance. There is no base resistance. It's 0 kilonewton. We have to set up to 0 kilonewton, and this is the other value, very, very important, is 100 kilonewton per square meters over the spin resistance of the ultimate shear force. These values came up from our analytical formulation. I mean, at the end of the day, we do not have to, we have to carry out our numerical analysis, but also all the time considering our analytical approach as the beginning. Okay. Then this is the model phase. As you can see, we have a phase of consolidation, and this is something very important based on my experience. If you carry out a model, I will go back. If you carry out a model of 150 meters 8 with a consolidation in one step, the model will fail, because the invert of the stiffness matrix is so high that the model say, hey man, I can't. So what you have to do is to, once you step the day, normally it's 10,000 or 100,000 or whatever, is to carry out a lowered factor and with a small lowered increment. This is very important because this allows us to reach the convergence, avoiding the numerical. Okay. Then going to the results. Okay, this is the results of Settle 3D. Almost zero settlement at 40-meter depth. So at the end of the day, we say, wow, at 40-meter depth, which is our pile, we will have a zero settlement. So at the end of the day, if I have zero settlement, I could consider some base resistance, no? What type of this setup that do not take into consideration consolidation and long term? This is a pure elastic calculation. It's in 3D. It's really nice. It's with a lot of colors, but it is something just to have a really rough number. Then we carry out the Plaxis model. The Plaxis 2D, we have more or less 10 centimeters or 0.10 meters settlement at 40-meter depth. So the second question is no, we can't use base resistance because we have a very high settlement at 40-meter depth. What is the problem of the Plaxis? There is no free effect, and the soft soil, depending of the cohesion, have the tangent of the friction of the soil. This is a very limitation of the soft soil in Plaxis instead of Midas. Midas is more similar to I would say to what Itasca flak use for soft soil. I mean, here, if we go back, sorry, here. Here we use the soft soil depending on the Young modulus, so depending on the deformation and the Boyd ratio here. So this is I would say the academic the academic approach and also the real approach we should take into account when we model the soft soil. Okay, so this is a limitation and should be analyzed. So should be take care of analysis of this because it can lead to some mistake. Then we have to the case study 1. This is no linear with no piles. So this is also to check the soil soft soil factual law with the laboratory test implementing the consolidation. So as you can see, if I'm implementing the consolidation, my consolidation at the end of the day, I have a value of almost half meter. So with this value half meter, I can't do only baseline, no? And then we have the other calculation here. This is the settlement, as you can see, half meter. So this is the analytical solution. This is the analytical solution, which is very similar to an odometer. At the end of the day, is similar to an odometer test. No, it's the Boussinesq and the semi-elastic space used by Boussinesq formula at the end of the day. And this is what Midas is giving us. This difference is exactly the difference between the elastic and isotropic material with the soft soil. So this difference is very important because with our model we are able to go further from the analytical solution and to have a real behavior of the soil. No, and then finally these are all the analysis in one graph, no, in one species. So we have the settle. As you can see, at 40 meters, we have almost 0. This is the Plaxis model. As you can see, if you model a soft soil with the Plaxis, you are having much more deflection, much more settlements, which implies that you will carry out a heavier design of piling, because it's not the same to have this profile of settlement than this one. And this is the Midas calculation. Okay. Regarding the comparison between pinned and hinged, these are the comparison in terms of displacement. They are almost the same, as is evident. The only difference is relating to the bending moment in the direction of this one. This is the bending moment directing on the direction of this direction, okay, or in this direction. Because here, if we are pinned, we are experimenting much more bending moment than if it is hinged. Why we carry out this analysis? Well, this is what the Eurocode 8 regarding seismic analysis recommends for in very high seismic area, because if we have a pinned solution, it is a good solution for seismic because the structure is more flexible. So when the earthquake will come, the structure will respond better because it's flexible. But from other point of view, can be too flexible, so can create a different number of plastic hinges, and the structure can collapse with a brittle configuration. No, this is the hinged, and which are the other option. No, the truth is between these two. Okay, so in other webinar, if we are interesting, we can speak about this configuration for earthquake of seismic area, and which is at the end of the day to realize, I would say, the semi-hinged connection. Okay. Regarding the skin friction, as you can see here, this is very important, because if we take the skin friction for all the piles we have simulate with Midas, we have to come out with the 100 kilonewton, 100 kPa we have established at the beginning. No, and this is also important to double check this value, not because we because this could be trivial to do this this checking, but sometimes is important because the model sometimes considering the interaction, and sometimes it's not taking these values. And then there is another issue I would like to highlight here is the values of the OCR. As you can see here, we have more OCR, so the soil is more confined, and then less by less we are going down till 1. No, this also has highlighted in this skin friction, where we have an increment of skin friction, in particular in some piles, but not in the central pile. So there is what we call an effect of a block. The pile is working not only a single pile, but is working like a block pile. No, this is very interesting. No? So this is the case study with the reduction of settlements from half meter to 15 centimeters. And also, this is important to study the 3D effects of the extension of the settlement. This is important because this desalination is not something built in nowhere, where there is nothing. This is built in some area where there are high pressure water, there is a decantation tank, there is other things that can be affected by the settlements on this area. No. Then this another issue. This the so-called block of pile. As you can see, the zone of influence of the pile is more or less starting 12 meters. So we have all this green zone, where is the piling are working not from structure, but are working like inclusion in soil. So here we are generating an area of increment of the stresses in the soil, which makes this solution at the end of the day, which makes this solution working. No? And as you can see, this is the excess of the pore pressure, which is directly related by the formula of Hooke to the settlement, because water is a Newtonian fluid, so it's directly related. So as you can see, this is this could be the profile of the settlement. No? And this is the end of the day the construction of the piling and the construction of the raft foundation. No, the second example instead is a pilot raft foundation of a tower in Mexico. I mean, as you probably know, Mexico City is a city like in Jakarta, where is sinking. This is due because of the exploitation of the phreatic level in this area. No? So all the structures are experimenting some sort of higher settlements. No, this tower was built here we were doing it here in AYESA, and the tower is 300 meter 8, and the surcharge is 13 kilograms per square meters. These are the South American way of represent is more or less 300 kilograms per square centimeter. No. The soil here also is very. I mean, it's not particularly the most beautiful soil in the world. This is the seismic velocity. We are about 500, a bit more what we have in the other case study. And this, as you can see, this is the water pressure. We have an increment, and we have the layer of the clay of Mexico, and then we have the deposit, and this is going maybe with the depth. No. Here, what we employed for this also is something interesting, because the slab has to work with an uplift pressure of 110 kPa. No. This is the seismic hazard, because also Mexico is very seismic, where we can speak it in another webinar. So here, instead of using the soft soil, what we use here was the camp clay. the model can play, as you probably know, is the model developed by Wood at Imperial College of London, and it is very useful when we want to capture the difference and the plasticity and or the yielding of the soil for over consolidating the place. No, the camp clay was basically done for the London clay in London. No, here what we had were at the end of the day was an odometer test and the CC and CS to evaluate the value, the possibility of the soil of expanding or reducing the volume, and then we have also the some tests for the young models. No, and with this we could create this table with all of these parameters. No, other issue important in the model camp clay. In Midas is very good model because it's depending on the pressure we have to set up at the beginning and from the void ratio. No, here also we have an allowable tensile stress of 98, almost 100 IPA. To take into account the suction can be produced. The suction is, I would say, the time the pore pressure is taking out from the over-consolidating clays. So it is also interesting to take into account this. No, the object of the target of this model was not to carry out completely the construction process, but was to in this case our colleagues, they were using the substructure method, so the method comparing the support independently, and to evaluate the so-called PY curves for piling. No, so this is the construction process. The so-called Milan method is top-down. We are doing piling, and then we are doing the top slab, and then we are executing while we are executing the basements, we are executing also the tower, the substructure. No, so our target from us was to model the PY curves for showing system. So in this case, it's not needed to carry out a complete 3D model, but with a 2D is quite good and quite easy and also quicker to carry out this model. No. This is the construction process. As you can see, these are the structure. So we are executing the piling from the surface, and then we are executing here the piling, and then less by less we are doing the slab, the base slab, and considering going down, we are excavating and executing the base slab, and then at the same time we are executing also the superstructure. No, okay. Relating the model, at the end of the day, this is the construction process. I don't know if I have here a video, but it is possible to do it, or try to do from my computer. But it's okay. It's just a video of the construction process. Let me just wait. Okay. Okay, I don't know if you can see my video. I hope so. So this is the construction process with the execution of the base slab, and this is also the model. Take time to open up. I hope you will. I hope you see my. Okay. So this is the model. Okay, and this is how is simulating the camp clay. Okay. This is relating to the FAS here, okay? And so this is the user defined. This is the pre-consolidation pressure set it to 100. Okay. So regarding the presentation, if we want to go to the presentation, so at the end of the day, this is then we can go back to this. So this at the end of the day was the PY curves we have to submit. So we have exactly the pressure, we have the equivalent correspondence, so and the bending moment, and these are the displacement versus the subgrade, the horizontal subgrade modulus, considering the different values, because we are in multi-layered soil. So for each soil and for each construction stage, we had a different subgrade modulus. No, and then conclusion. This what I would like to open up a discussion maybe with you. A non-linear solid structure interaction are more required in engineering practice because of the value engineering in foundation, because all people who are working in a consultant or in construction, we need to carry out some sort of value engineering. In some cases, carry out a numerical analysis can bring extra data to a problem, or also find a different solution, or also I would say to get far from the analytical calculation. No, combined qualified foundation are very common because of their versatility and because of their very used, and in some cases they are used also when they are not so required. And then regarding the case study, we have employed Midas GTS to considering piling 100% working in soft soil. And in case 2, we consider also the combined vast foundation of a building tower. No, I decided to bring these two case study to also highlight something relating with Midas. First of all, that Midas is not only a 3D model, it is 2D models also. 2D is working very good. It's working comparing to other software. Is working faster. I mean, comparing to Plaxis, it is possible from 2D to extrude directly to 3D without acquiring another license. So it is very, very versatile, and it is very, very helpful. And this is what I would like to share with